Welcome to the Vigenere Lab demonstration. The Vigenere Lab is a cryptanalysis lab to help you understand how you would do cryptanalysis against the Vigenere cipher. The lab software opens up and gives you the opportunity to pick the ciphertext file you want to use. In this case, for the demonstration, we're going to use file demo2.txt. So I just click on that file, and this is like any normal window for opening files. This is being recorded on an Ubuntu machine, so it might look a little different than a Windows machine, but the lab software will operate the same way. So once that's done, we've downloaded the encrypted text into our encrypted text window, and it has a scroll bar. The text is fairly long because that's required for a Vigenere cryptanalysis. I'm not going to get into the details of the Vigenere cipher because you can read that in your textbooks. But as you probably know from your textbook, the first thing that needs to be done to do cryptanalysis on a Vigenere lab is to do a Kasiki examination. A Kasiki examination is trying to find the distance between repeating patterns, because the distance between repeating patterns may indicate the length of the crypto key that was used to encrypt the message. The other possibility, though, is that it's just a random case where different alphabets were chosen and the sequence of the alphabets just happened to make the pattern again. Of course, the longer the pattern, the more likely it is that it represents the key length. So let me do the Kasiki exam on this, and we'll look at the window that opens up. So this is a Kasiki examination window. It's got a number of columns. The first column is marked sequence, and that's the pattern that we're looking at that repeats some number of spacing apart within the ciphertext. Now, ADWX must have a spacing that's beyond 20. That's why it doesn't show up on the table. And so 2 is a spacing of 2. 3 would be a spacing of 3 between repeating patterns, etc. Now, the key length could have a repeating sequence that was any factor that divides evenly into the key length. So for instance, if your key length was 5, 5, 10, 15, 20 would be where you would kind of expect possible key length patterns to be. But it would be the same if the key was 10 characters long. So what we want to do is we want to look down the columns and see which spacing is most often scored. And it's this overall set of spacings that will be most accurate. It'll remove whatever's due to just randomness. So if we look here, and we'll scroll down to look at all the patterns, you can see even on this first part, though, that the spacing 5 seems to be fairly predominant over the other spacings. But let's not just use a part of it. So we'll scroll down, and yeah, 5 definitely seems to be the strongest factor of any of them, with some of the others being close. Now we'll choose 5 because it seems fairly strong in this demo text. Now I can close the window, or I can move it over to the side and check the spacing again later if the choice I made is not the correct choice. I'm going to close the window because 5 was very dominant So I'm going to dismiss the window here. And the next thing, after you do the Cacique examination, enter the key length in the Cacique examination below. So I'll enter 5 here, because that's the key length that looked like it was definitely the best possibility. I can always go back and redo the Cacique examination. Will come up again if I so need the data. Now the next step is to do what I call an ETA-OIN analysis. ETA-OIN are the 6 most frequently scored letters in the English language, with E being the most frequently scored, T next down to N. There's also another 6 at the other end of the alphabet that are the least frequently scored. And if you look at these 12, you get a very, very good sampling without having to sample the whole alphabet. So the ETA-OIN analysis does a little bit of magic on it. So let's do the analysis and then we'll talk about it. So we have one window opens up for each of the 5 positions of the key because we selected 5 as the length of the key. So if we look at this first one, this one where I have my mouse, it says letters for key position 1. If you look, the second one says letters for key position 2. They're all staggered so they're easy for you to see. So what this is a score for the letter alphabet. And in other words, the higher the score, the more likely that's the alphabet that was used to encrypt the letters in position 1, and that would be every 5th letter. So 1, 6, 11, 16. So we get a subset of the whole encrypted text based on the length of the key. So it's taken all of these subset characters and it's done a frequency analysis. The frequency analysis, then we look down this column and that's going to tell us which alphabet is most likely the right one. So if I go down here, I look, we got 2, 2, 3, 1, 4, 4 is the highest so far, 1, 2, 2, 0, 3, 3, 8. 8 beats 4, so that's the highest. I got 1, 2, 2, 4, 3, 3, 3, 0, 2, 2, 2, 0, 5. So 8. 8's my most likely letter. Again, all of this is based on probability and statistics. There is some guessing, but rather than making just a random guess and having a chance of being half right or half wrong, at least with this, we've got an educated guess. So in this case, I'm going to sit here and write down the letters. So column 2 in the ETA-OIN analysis tells you what letter represents that alphabet. And it happens to be the letter that's first in the alphabet. But that letter, L in this case, would be the one I would use as my potential key. So since I think L's one stands out far beyond the other letters, I'm going to dismiss this one. These are also all redoable. Just hit the ETA-OIN analysis key and you'll get these over again. Now in the second position, I'm going to look for the most frequently scored letter. It looks like 9 here is the highest if I go down this column. I'll double check because it's easy enough to miss which one it is. Okay, and that letter is E, so that would say the next character would be E. Make sure that I'm correct on that. Yep, so I'd say it's E. And if I'm wrong, I have to go back then and try my second most likely guess. And so it's a little bit of fiddling sometimes that has to be done. It's just the way it is with cryptanalysis of this particular cipher, but the tools work fairly well. All the lab software does is remove all the drudge work and the monumental amount of manual calculations that would be required to get these numbers. So now we're looking for key position 3, so this will be third letter in our key. And again, we got a bunch of 3s, 4's the highest, 5's the highest. I go down here, keep looking. Oh, I see 10. 10's the only 2-digit number, so that's almost a given. That's way ahead of everybody else. So then the third letter in my key would be W. So now I'm going to look at position 4. And I just repeat this process over and over again for each letter. Here it looks like I far exceeds all the other alphabets. So I would be my next letter guess. And now for the last letter, position 5 letter, I look down, I've got, okay, looks like, oh, 9. Looks like 9's the most scored, best score on the sheet. So that would be my last letter. Now again, this key phrase, oftentimes people are going to choose a phrase that's easy for them to remember. Although if you really wanted to make a secure encryption, you might choose a phrase like, I went to see my brother yesterday, and use that. But for purposes of the lab, I'm not going to give you something monstrously like that. A lot of letters and key positions to look through, and you're not learning anything through that. So now I'm going to enter in the letters I think make up the key. And it doesn't matter if they're capital or small letters, it doesn't care. I'm type it L-E-W-I-S. Now if this is the correct key, when I hit the decrypt button, in a decrypted text box, you should see readable English. To make this lab a little easier, I did not remove exclamation marks, periods, punctuation marks, and I did not remove the spaces between words. So I left it so it's much more readable for you guys when you finally found the answer. Unlike some of the others where real cryptography, you would usually block them into some grouping like 5 or 6, and you'd have maybe 5 or 6 of these blocks on a line, and you'd have 5 or 6 lines and then a blank line between them. So it makes it much harder to get any information from it. But for this lab, the tool is going to give you a pretty accurate approach to solving it. So I didn't think it was that important, and I didn't want you to have to try and figure out a long piece of text. So now we hit the decrypt button and we hold our fingers crossed. And in fact, I guess we were right, because you can read either the well was very deep or she fell very slowly, for she had plenty of time as she went down to look about her and to wonder what was going to happen next. I don't know if you can figure out from the first sentence, but the quote is from Alice in Wonderland by Lewis Carroll. So this is the process described in your textbook, where you do the Kasiki examination, then you do the ETA OIN analysis, and then you try the key. There are other ways you can do it, because Vigenere cipher just uses 26 Caesar alphabets with one shift for each of the alphabets, and the last one being the same as the original English alphabet. But this is a technique I think is more realistic. Most cryptographers tend to use frequency analysis over trying to, just brute force a Caesar cipher. So this is the end of the demonstration for the Vigenere Lab. Thank you, and I hope this makes it easier for you to use the tool.